right. Hello, welcome to Jeff's DSUA111 section for, I'm late on it this week, but the whatever section covers lab 10, that's what we're doing today. The section to cover the optional lab 10. So yeah, last week we covered lab 9. This week we'll cover lab 10, but both lab 9 and lab 10 were optional. So hopefully you're spending most of your time on your projects, but yeah, lab 10 can give you an extra boost in your grade. So I'll share screen. Yeah. All right. So we go to rcnyu.org and we spawn our server. And hopefully it's about to launch. Cool. I have to change this real quick because I already did a practice run. But on your end, you'll go right to the assignments tab, click fetch for lab 10, and then you can just open it right from that panel. So yeah, this week is regression, but very specifically like the underlying details of regression that you don't necessarily need to know for the project, right? A lot of there's been a lot of confusion in like emails and office hours and stuff where a lot of you are manually computing things like the regression coefficient or the confidence intervals, things like that for the project. For the project, you actually don't need to compute those things manually, meaning for the project, you can just use the stats models package that I went through in my video on regression, like the special section video. These, like the things that Chris has done in lecture and this lab are kind of going into the details of regression, but you don't need to do any of these computations really. Stats models will give you the R squared, they'll give you the confidence interval, the test statistic, the p-value, everything. So like the point of the project is not to have you compute test statistics or like do bootstrap or anything like that. Point of the project is essentially just so that you have experience going onto the web, finding a data set that's interesting to you, and then finding, estimating some relationship between variables. So I just wanted to point that out because a lot of people are doing a lot more work on the project than you need to do, right? But so like the stuff in this section, we're gonna learn some of the nuts and bolts of regression, but yeah, just so you know, you don't have to do any of the stuff that we're doing in here for the project. For the project, just use stats models package. Cool. So yeah, we run our import statements, and the introduction just says basically different theories of how old the universe is and how we can backwards infer how old the universe is by looking at the speed at which planets are moving away from Earth, right? Because the point of the Big Bang is that all matter started in a single point, and then there was a big bang, and all the matter is now rapidly like blown apart, and it's getting further and further and further from the center of where the Big Bang happened, but meaning that from the frame of reference of any planet, for example, Earth, right? We can look out at all the other planets and see how fast they're traveling away from us, start to get an estimate of how old the universe is from that. So yeah, Hubble's law is that every star or planet far away from the Earth is moving away from the Earth at a constant speed. So we work backwards to the time when everything was in the same place, we can estimate the age of the universe. That's the gist of it. So when we run this cell, we get this simulation, right? So this yellow dot is the sun, and the blue dots are other stars that we can observe like from our solar system. And so this is the state now, whereas if we went like, 1.5 years into the future, all the stars would be further away. Whereas if we went backwards, the stars would be closer, right? If we go backwards far enough to the beginning, all the stars will be in the exact same point. So from the example above, when can you say the simulated universe started? Where does t begin? In this case, we found it out by just moving the slider back and forth, and we see that at -2, we've gotten to a point where every single is at the same point, right? So that's like the start of the Big Bang. The Big Bang happened from this point. So that's t equals -2, 2 years in the past in this model. So the answer is 1, 2 years ago. Now, after 5 years in the simulation, stars with longer arrows are further away from the sun. Why? The idea here is that the arrows, there's two properties of the arrows, right? One is the direction that they're pointing in, but the other is how long the arrow is, right? And so you get two pieces of information from each arrow. Let me just go like to here so we can see them better. So like this arrow right here, this arrow right here is much longer than this arrow right here, and that's just the length of the arrow is the speed, right? It's a measure of the speed. So like if it wasn't moving at all, the arrow would be infinitely small. It would be 0 length. Whereas if it was moving at, 1,000,000 miles per hour, then the length would be 1,000,000. So that's what the arrows represent. And stars with longer arrows are further away from the sun. And that's because, length of the arrows represents the star's speed. So stars with longer arrows are moving faster away from the sun is the answer. I don't really understand the other two that much. Number one we can throw out because we know the length of the arrows does not represent the movement, right? It does not represent the direction of movement. The direction of movement is based on where the arrow is pointing, right? If it's pointing this way, the arrow is moving in that direction. If it's pointing this way, then the star is moving in that direction, whereas the arrow length is the speed at which it's moving. So we narrow it down to 2 and 3, and then we know that longer arrow means traveling faster, right? So the only one that makes sense is 2. An analogy to Hubble's law. So now we say, okay, at some point in the past, our friend Sheldon started driving a car going 60 miles per hour straight east. And Sheldon was going 60 miles an hour the entire time. Sheldon started right here where we're standing and we haven't moved. And Sheldon has been driving at a constant 60 miles an hour away from us, right? So we can kind of use the slider in the same way as we did before, right? If we run it back all the way to the beginning, Sheldon is right on the exact point where we are, but after 2 hours, right, Sheldon is some certain amount of distance away. And we want to know how long he's been driving, but we forgot to record the time when he left. So if we find out that he's 120 miles away and he's been doing 60 miles per hour the whole time, we can infer that he left 2 hours ago, right? It's like algebra. You're solving for t. And so, one way that we can compute this number is by fitting a line to a scatter plot of our locations and speed. So we have this little example where we have us, right? We are moving away from ourselves at 0 miles per hour because we're not moving at all. Our distance from us is 0 because it's us. And then Sheldon has been moving at 60 miles per hour and is currently 120 miles away from us, right? And so we can plot this, we can make this plot that just shows like we're here, Sheldon's here, and we draw a line between them, right? And the slope of that line is the speed. Because it's rise, right? If you remember like from algebra or pre-calculus or some class, the slope of a line is exactly its rise over run, which means like you go a certain amount up in the y-axis for every amount that you go to the right on the x-axis, right? So in this case, the slope is rise, meaning change in distance from us, over run, which is speed. And so if we compute the slope, that's how we get how long Sheldon has been driving, right? Because the y-axis unit is miles, like we see here. The x-axis unit is miles per hour. If you divide miles by miles per hour, and you do division tricks, you get that that's hours, right? The unit is, so the unit of the slope is hours. But that's assuming that we know exactly Sheldon's position, right? We know exactly his distance from us, but let's say we just had estimates. Like we went down the road and we asked people like, oh, how long ago was Sheldon here? And they estimate it, right? We might have a data set that looks like this, where each point is an estimate of his distance from us. And yeah, each point is a distance he is from us, and each point on the x-axis is a speed that he was driving. So yeah, sorry, I should say I skipped over a lot, but yeah, now we have the speeds and distances from start for 100 drivers, right? They all left the same starting location at the same time, driving in a straight line away from the start. So they all started at exactly the same time, but we didn't get to observe what time they left. We only got to observe these noisy estimates of their distance from us and their speed when they're at that distance, right? They're noisy because again, someone like 60, for this point, like someone 60 miles from us, say maybe calls us and says, it looks like they're moving about 35 miles per hour, right? So question 3 asks you, by looking at the fit line, estimate how many hours earlier the drivers must have started, right? So even though we have a bunch of noisy estimates, we see that the line of best fit actually fits it pretty well, right? So we're going to use our line as our estimate of the relationship between the speed moving away from us and the current distance from us, right? And so if we want to estimate how many hours the drivers must have started, we do the same thing that we did up here with Sheldon, right? Before we drew a line from like 0 out to Sheldon's point. Now we draw a line starting at 0, but it's the best fit line, right? And so just like before, how the slope of this line told us how many hours Sheldon has been driving. Same thing here. Estimate how many hours earlier the drivers must have started. It's just the slope of this line here. So if we remember that slope is rise over run, we can see that, and we're estimating here, right? There's no way without like going into the plot and seeing the exact pixel values and stuff like that. There's no way to get the exact slope, so we're just going to estimate it by looking at it, right? So from what I can tell, basically when the speed is 10, right, when the x-axis value is 10, the distance from us that is estimated by this best fit line is about 15, right? And so what I would say is it's slope, right, which is how many hours earlier the drivers must have started, is like 15 miles over for every 10 miles per hour, right? So about 1.5. So from this line, from these noisy estimates of the distance and speed of the cars, we end up with an estimate that they must have left about 1.5 hours ago. Right? That's kind of the 1.5 hours is kind of the estimate that makes the most sense given the best fit line through our estimates. Cool. And now we want to do the same thing for the universe, right? So now the cars were just a metaphor. Now the car is a planet. And the starting point is the point of the Big Bang. So we get another data set called novas, close novas, that has observations of a bunch of stars, right? And for each star, we have the distance from us and the speed that it's going at, right? And when we plot it and we get a best fit line, again, we see that a line actually does quite well at fitting these points, right? Yeah, so same way that we did before with the cars, we're going to look at this plot to estimate the age of the universe, right? It's just going to be, we're just going to estimate the slope of this best fit line. So, and it makes the very good hint that you need to make sure you get the units right. Right, so we'll get to that. But basically, I'm going to eyeball this, and I'm going to say, basically, by the time that our best fit line has reached 100 on the y-axis, it looks like it's about 7 on, or sorry, 0.007 on the x-axis, right? Like I just kind of start at 0.007 on the x-axis and I move my mouse up. That looks like it corresponds to about exactly 100 on the y-axis, right? So you might think, okay, so then Q4, our estimate of the slope is 100 divided by 0.007. And it's close, but the unit here is in million parsecs, right? So it's not just 100 parsecs, it's 100 million parsecs. So we have to make sure that we get our units right? Or you're gonna get this question wrong. Because the numerator is not 100, it's 100 million. So 100 and then 6 zeros after it. And if we print out what that is, we actually get, it's about 14.29 billion, right? Because it's 14 and then there's 1, 2, 3, 4, 5, 6, 7, 8, 9 digits after it. So we have used our best fit line through these observations of planets to come up with an estimate of the Earth's age as, or sorry, the universe's age as 14.29 billion years. And you can, yeah, you can like go through it and think carefully about why we needed to put 100 million rather than just 100 to make sure that our, and that we end up with units that are years rather than like your thousands of years or millions of years, right? This unit is in the base unit that, this number is in the base unit that we want, which is just years. Cool. So yeah, we want to calculate the slope. We estimated it here, but we remember that like, so this line is generated by running a regression, right? When you run a regression of the y variable, in this case distance, on the x variable speed, you get an estimate of the slope. Well, you get a best fit line, which has a slope and an intercept, right? So you get an estimate for the slope and intercept. And like the way that regression works under the hood, like I said at the beginning, going a little under the hood, is that the best fit line is just the line that minimizes errors, right? So you can imagine like the way that a computer or anyone, like the way that a small child could eventually get to this best fit line without using like advanced matrix algebra and stuff is just put a random line and then measure how bad that line does at predicting the y value, distance from the x value, speed, and then just pick another line and then compute how badly it does, right? And pick another line and pick another line. and you would start to see a pattern that, like, if your line was up here, it would be way over predicting everything, right? So you'd say, okay, I want to make the slope lower, but then your line might be down here and it might be under predicting the distance for all the speeds, right? And so eventually you would see that there's actually exactly one line you can draw that's the line of best fit that minimizes, it like balances under predicting some with over predicting others to optimize the error, right? It's the lowest possible error, where error is like, just pick one of these points, and right, so like here we have a point that it's at about x equals 0.013, right? And now this line predicts that its distance is going to be like 180 or something, whereas its actual distance is 150, right? So the error there is 30. But this is the line where if you add up the errors for all the points, that you can't come up with a line that does better in terms of errors. Because if you tried to like move it up, right? If you tried to slant it up a little bit more, you'd do better on these points above the line, but you'd do even worse on the points below it, right? So it is the line that strikes the optimal balance between over-predicting and under-predicting, averaged over all the points. Cool. So yeah, the error is just measured by a supernova's actual distance from Earth minus the height of the line at that supernova speed, right? What I've been calling like the distance that's predicted by our best fit line. So we're going to write a function that's going to compute this error, right? It's going to take a table like close novas. Well, it's a data frame, right? When you see the word table, read data frame. There's an old version of this class where they used tables, but we've converted everything to data frames. So, but that word is left over from older versions of the class. So we have a table like close novas, and we have the slope and the intercept of a best fit line, right? And so given a table, or in reality, a data frame, right? Given a data frame and a slope and an intercept, which gives us a line. So essentially, even though it's 3 arguments, just think of it as like, have a table of actual observations, and then you have a line, and you're trying to see how good this line does, right? Errors, you're trying to see how bad the errors are of this line. So what we can do is we can say, okay, our observed y variables, right? Our observed distances is just, we just go into the table and we take this variable, right? It has, the table actually has like the observed distances in it. Distance in million parsecs. Cool. So that part's easy. That's just saying like our observed values are just that column, that distance column. But now we need to compute all the predicted values, right? And to do that, we remember that a line is defined as like the intercept plus slope times x, right? And so our x value here, in this case, is speed. So the value that the line's going to predict is going to be the intercept plus the slope times our speed values. X per year. Right, so meaning like they gave us the intercept and they gave us a slope, and that means that by taking every value in our speed column, multiplying it by the slope and then adding the intercept, we get what the best fit line would predict for that point, right, for that speed. Cool. So that's the, like we just did in math, what I've been doing by hand here, which is like, okay, if my speed is 0.008 and I go up on the line, right, that line also predicts a y value. So about like 120 here. This is just doing that with math for every single entry in the table, every single speed entry in the table. Cool. And then we just return that difference. So that's our errors function. And now using the errors function, it wants you to compute the errors for a line. Let's say we just guessed, okay, maybe we're going to guess a best fit line with a slope of 16,000 and an intercept of 0, right? And so now we can use our errors function. We want to give it, the first argument is table, so we want to give it the close novas table. The second argument is slope, so in this case we want to give it 16,000. And the third argument is intercept, which is 0 in this case. So that's our call, but I'm going to also print out example errors just so you can see. All right, so this is saying that like for the first point in our data set, it over predicts it by about 22, right? Second point, over predicts it by 28. Third point, over predicts it by 28. Fourth point does okay. It gets almost exactly right, but you can see that we're over predicting a lot. And if we look at a scatter plot, yeah, you can see. So like 0 would mean that we perfectly predicted that point, right? Meaning if a point is on y-axis, if a point's y coordinate is 0, that means that for that point, we were able to perfectly predict the distance from the speed, right? Whereas if it's negative, that means we over predicted the distance. So yeah, you will find that the errors are almost all negative, so that our line is a bit too steep, right? It's predicting much higher values than the actual values, which is why the difference will always be negative. So we have a helper function called fitLine. It takes a table of data, and then it also takes a function to compute the error. And now this is like, it's really weird because the assignment doesn't really explain like what's happening here, but what's happening is kind of the example I was giving before of how like, okay, well, you can just pick a random line, put it down, see how badly it does, and then say, oh, okay, I guess I should make it steeper or less steep, right? And you can like keep doing that. As long as you have a table of data, right? And then an error function, right? We wrote an error function up there. As long as you have those two pieces, then computers can like run an optimization routine, an optimization process to find the best fit line, right? And like, it seems kind of weird because, at least it seems weird to me, because you could just like mathematically compute the best fit line rather than like guessing lines and like being like, oh, that line sucks. That's not a good line. Let me try a different one. Let me try a different one. Like it seems inefficient, but it turns out that line of best fit is kind of a special case where you can compute it mathematically. Actually, for like most big problems that computers are solving, it actually does have to just like guess a solution, see how badly it does, and then just try a different one. And after it tries like thousands and thousands of different solutions and sees how good or bad they do, it starts to get a feel for like, okay, the solutions around this region, you know, like this, like it starts to figure out like, oh, okay, the slope should be somewhere around here and the intercept should be somewhere around here. And turns out that's how like, you know, all the AI stuff that you hear about, that's how you train those models, is the model just kind of guesses values for its parameters, and then you tell it how badly it did, and then it tries again, and tries again, and tries again. So even though it seems inefficient, it's actually how like all neural networks and all that stuff, it's how it works, right? It's only inefficient in this case because we know this is one of the few cases where we don't have to do that arduous process to find the best fit line. The best fit line we can compute using math, and like you can go Google it. There's like a formula where given a set of points, you can just immediately compute what the best fit line is without like guessing and checking. So that's what this fit line function is doing. Anyways, it's saying, all right, give me a table and give me an error function, and I'll try a bunch of lines and I'll find the best one, right? So that's this helper function that you're given. And what that means is like, instead of, you know, like I said, instead of going and Googling the formula and solving for the best fit line, we're just going to say, all right, I don't know the formula, but I have this fit line function where I can just give it a way to compute errors, and I can give it a data set, and it'll just guess a bunch of lines until it gets the best one. So all we need to do is finish this mean squared error function, right? This is the function that we're going to give to the optimizer which in this case is fitline. Fitline is our line optimizer. So we get that it has mean square error takes in, observed values and predicted values, and then it just finds their difference and squares it. If we were in a class, I'd ask people like, why do you think that it squares it? We've seen a couple examples so far in this class of why you would do that, but it's basically just so that like over predictions and under predictions don't cancel each other out, right? Like if you over predict 1 point by 20 and you under predict another point by 20, if you didn't square the numbers and when you added those up and averaged them, like the average error, if one is over predicted by 20 and the other is under predicted by 20, is actually 0, right? Because negative 20 plus 20 divided by 2 is 0. But when you square it, it takes into account that like we don't care about the direction of the error. We just care that there was an error, right? We want to sum up all the errors. So when we square it, then negative 20 squared is 400 and 20 squared is 400. So there you get 400 plus 400 divided by 2. 400, right? It's the average error there. So yeah, that's why we do the squaring. And we've talked about it in prior sections, but like you could also do absolute value. But this again goes into like AI stuff where it turns out that neural networks have to take derivatives of like the error functions to see what direction it should go in. And if you've taken calculus, you might get that. If you haven't, don't worry. But the point is that the squared error has a simple derivative to compute, right? If you've taken calculus, the derivative of x squared is just 2x, right? Meaning that if we know the squared error of something, you can just take 2 times that, and that's its derivative. Whereas the absolute value function actually doesn't have its derivative is not defined everywhere. There's a kink in it at 0. Don't worry about what that means. But the point is like, even though you might say like, oh, it seems arbitrary, like when do we use squared and when do we use absolute value? Actually, like in neural nets and machine learning and all that, you're just pretty much always going to be using squared rather than absolute value because of calculus. So anyway, we already have a line in here that takes the errors and squares them. So, but we don't want the total squared error, right? We want the average squared error. So all we need to do is do np.mean of the errors squared, right? Meaning like errors squared is going to be a big list, right? Where each element of that list is how badly we did for each point, right? So like the first element of error squared is going to be our error for the first point, and the second element in error squared is going to be our squared error for the second point. So we don't, the computer can't do anything with a big list of errors. It just needs like a single number that says how badly that line did. So in that case, we just take the average of all the errors, right? Average of the squared errors. That's like on the whole, how badly the line did, right? So now that we've written this function, right, we just return the mean of the squared errors. We can provide our data table along with our mean squared error function to our line optimizer, right? And when you do this question, personally, I found it ultra confusing because it's saying like, oh, set best line slope equal to something and set best line intercept equal to something. But actually, you'll see that fit line, right? We're eventually going to call fit line our line optimizer. It returns like 2 things at the same time. I'll show you what I mean, but basically I'm going to comment these lines out for now, like all the lines in it, and I'm just going to show you what the output of fit line looks like. So fit line takes in a data table, in this case close novas, and a function that it uses to compute how badly a line is, right? In this case, we'll give it mean squared error. And I'll say like fit line output equals that, right? And then I'm gonna print fit line output so you can see what it looks like, right? And it's kind of weird, right? So it actually gives us 2 values. It gives us a slope and an intercept at the same time. So it's kind of weird, like you're not you're not calling fit line twice. Like even though there's two lines here that it wants you to fill out, really you're just calling fit line once. And then the first element of its output is the slope. So now I can uncomment this, and I'll uncomment this while I'm at it. And I'll say the slope is the fit line output. It's the first thing in here, right? So the thing in slot 0, whereas the intercept is the second thing here. So fit line output 1. And now it'll work as we wanted, right? So the estimated slope is about 14,094.5. So now that we've like, rather than eyeballing it like we did up here, right? Where was it? Yeah, we eyeballed it up here and we estimated like, okay, it's about 14.29 billion years old. Here we use like an actual line optimizer function that finds the best slope and best intercept. And through that we get 14.0945. So our estimate wasn't that bad. The current best estimate though is 13.799, right? So we got closer, but we didn't get that, meaning if the real thing is 13.799, then we improved when we went from eyeballing it and getting 14.29 to actually like computing the best fit line, estimating using that line, and getting 14.09. We're much closer to 13.8 billion years. So yeah, basically it's like the reason that an answer might be a little off is because we're using a sample of only some of the supernova, right? Our sample isn't random because astronomers can't just like sample stars from all over the universe. Presumably the stars closer to us are easier to measure, right? So instead of like trying to compute just a point estimate, right? That's what it's called when you just say like, I guess that the age is 14.08, right? Instead of guessing a point estimate, we're gonna get a spread, right? We're gonna get a confidence interval, which is like a fundamentally different thing because a confidence interval is not saying like, oh, I estimate this quantity to be X, you know? In this case, I estimate the age to be 14.09 billion years. Confidence interval, right? It's like, oh, I estimate that the age is somewhere in this range. So it's kind of like, it's a more statistically principled thing because you're actually explaining to the person that, oh, there's like random variation that I can't, that like my estimate, my model here, my linear model isn't taking into account, right? Meaning the line of best fit would only like perfectly tell us the age if all the points actually laid on a line, right? But they clearly don't, and that's why we get errors. And so even though we picked the best fit line, we're not accounting for all the error. So as a way to kind of like be more honest that there's error that we can't account for in our linear model, we will, compute a confidence interval and just report that instead of reporting a specific like prediction for the age. So yeah, now we're going to use our errors function that we wrote way up here, that given a table and a line, right, where a line is defined by two quantities, a slope and an intercept. So given a table and a line and information about a line, it computes how badly that line does at predicting the value, the distance values in the table from the speed values. So now we're going to use our errors function on the best fit line that we found, right? Using our line optimizer. So in this case, we want to call errors where the first argument, as before, is close novas, but now our estimated slope is best line slope, right? Best line slope. And the intercept we give it is best line intercept. Best line intercept. And so, yeah, now, so remember like before we called errors on like a random line we picked, it was like, I don't know, let's just guess slope is 16,000 and intercept is 0, right? And we saw that this graph of the errors of using that line is like, tells us like, oh, we're over predicting, right? Most of the points, most of the errors are negative, they're down here, right? Now, if you've kind of assimilated everything we've talked about, you'll know it's like what I was saying earlier, how the best fit line is the one that's gonna balance the over predictions and the under predictions the best, right? So we know we've kind of like hit the best fit line when we plot the errors like this, and we see that there's kind of no systematic bias between over predicting and under predicting, right? So that's kind of what this part is trying to get at. Like, how does the scatter plot of errors compare to question 6? Well, in question 6, we saw, oh, we are over predicting most of the time, right? Whereas here, we're only over predicting for about half the points. For the other half, we're under predicting, right? That's like, what qualities should the best fit line display in the scatter plot of the errors? That's what I was talking about. They should like balance. If you notice that, like if you pick a line and you're like, I think this is the best fit line, but you notice that systematically you're under predicting more than you're over predicting, right? Then you probably don't have the best fit line. But in this case, it used a mathematical tool to just like guess a bunch of lines and then compute the error until it found the best one. And that's how it found this line that like optimally balanced over predicting with under predicting. So yeah, it looks as it should for a best fit line. It looks like it perfectly balances over and under predicting. Okay, so it's time to bootstrap, right? So that's how we would get our confidence interval, is we would run the bootstrap to get 1,000 different estimates of the age of the universe, and then our 95% confidence interval is just all the values from the 5th percentile to the 95th percentile, right? But actually, like, all of the code here is written. Like it says, it'll take the code a few minutes sorry, you should run it ASAP because it will take a few minutes to run. But while it runs, I'll just explain what's happening, right? So we have 1,000 replications. Each time that we're resampling, we are creating a new like bootstrapped sample that's the same length as our original closed novas data set, but we're sampling with replacement, right? And so like we've seen in past labs and homeworks, when you sample with replacement, the same, like a single data point from the original data set, the original closed novas, could appear twice or 3 times in our resample, and then other points from the original closed novas data set might appear never, right? They might never get sampled. So like every resample is kind of like a fake subsample from our closed novas sample, right? And so that's how we'll get the variation. It's like sometimes we'll be oversampling certain stars, sometimes we'll be undersampling other stars, and we'll see like how robust our estimate is, right? Meaning like, oh, if I throw out these stars and then I estimate the age of the universe, but I exclude those from my sample, how well do I do? And then, you know, if I had like 10 stars that looked like this one star, how well would I do, right? So it's kind of, bootstrapping is kind of like generating like showing how robust your estimate is. And by that, I mean like, if you found that if you throw away 1 star, your estimate totally changes, that's a really like volatile estimate, right? It's like, oh, that's kind of weird because like maybe if I added 1 more star, like I went and I took my telescope and I sampled 1 more star, we wouldn't want that to completely change our estimate, right? So kind of like the better our estimate is, the less variability will happen as we oversample some things and undersample some things. And that's the logic of the bootstrap here. So cool, it's finished. We've done 1,000 resamples, and for each one we have found the best fit line. And now, so we could print out our estimates, right? Estimates, age, I'll just print the first like 50, let's say. Right, so it's like for this resample of the stars, we estimate 13.8277 years. Whereas for this one, we estimate 14.1929, right? But they're all kind of like within a range between, just eyeballing it, it's a range of like 13.8 to 14.3, right? So that's what I was talking about, where it's like it's fairly robust in the sense that, well, it depends on like how specific you want to get, but it's not like, oh, if we throw away 2 stars and we oversample 2 other ones, suddenly our estimate goes to like 2, right? That's kind of what I'm saying by robustness. So yeah, now we'll get our confidence interval by just taking our 1,000 estimates from our 1,000 resamples, and we'll compute the 5th percentile using calculate percentile helper function, right? That just says, give me a list of estimates. So in this case, estimates age. And give me a percentile you want, in this case, 5. Similarly here, we want calculate percentile. Estimates age is the list, the array containing all the estimates, and then, but here we want the 95th percentile. And you can actually print the, I'm gonna print these so we can see percentile 5, percentile 95. Cool. So the 5th percentile is 13.68 and the 95th percentile is 14.44, right? So now, like, even when we resample 1,000 times, 90% of the time, we get an estimate of the age between these 2 values. Cool. And we can plot that to see that, great. The red dot is like what actual astronomers have computed the age of the universe to be, given like the best available equipment and data and whatnot. Whereas here, you know, we have a histogram of our estimates. So remember, like when we just did a point estimate, when we just said like, okay, I guess the age is blank, right? When we use our best fit line to compute just a point estimate, we got it wrong, right? It was closer than our eyeballed estimate, but it was still wrong because we got 14.09, whereas the actual age is 13.799. So it's kind of showing you like the upside of the point estimate is that, you know, you have an actual amount that you can report to someone, right? Like your boss says, like, I want an estimate of blank. You can give a point estimate is like an estimate of that quantity. Whereas, but you might get it wrong. Whereas here, if you report the 95% confidence interval, you get it, you know, quote unquote, right, because it is true, like the true age of the universe, 13.8 approximately, 13.799, it is in our 95% confidence interval, right? So it's like, that's kind of an illustration of why we have these confidence intervals, because we might say like, oh, wow, I don't have enough data to produce a point estimate that's like right, you know, like I don't have enough data that the data tells me, oh, I got an estimate of 13.7999 years, but we can use bootstrap and resampling and stuff to get a confidence interval. And in this case, confidence interval worked out because the true value is inside our confidence interval. So yeah, that's how you do this lab. And yeah, you can compare with like this project of astronomers, which estimated it to be 13.799 plus or minus 0.01 billion years. Submit it and get those free points.